Welcome to the wonderful world of membranes. I'm Jamie.
And I'm Dr. Nano.
And today we are diving into nanofiltration.
Or as I like to call it, the Goldilocks of filtration.
Not too tight, not too loose, just right. Dr. Nano, so what makes nanofiltration so special?
Nanofiltration refers to a specialty membrane process that rejects dissolved solids in the approximate size range of 1 nanometer, that is 10 angstroms, hence the term nanofiltration. It is a membrane filtration process that is perfect for separating divalent and larger ions from water, while letting smaller monovalent ions slip through. It's kind of like a bouncer at a club, only letting the VIPs, or in this case, sodium and chloride ions, in. Jamie, can you please tell us more about nanofiltration?
Oh yes, nanofiltration is a liquid phase separation process for removing dissolved solids carried out by means of membranes. It is one of the 4 membrane technologies that use pressure as a driving force to effect separation. The other technologies include microfiltration, ultrafiltration, and reverse osmosis. And that's why it's great for softening water. But there's more to it than just size exclusion. Let me introduce you to the Donan effect.
We are sure you would want to know how this works. The nanofiltration membrane has a thin film composite structure with a porous support layer and a thin selective layer. This selective layer does the heavy lifting, letting water molecules and small solutes through while rejecting larger solutes and multivalent ions.
So it's kind of like a super smart sieve?
Exactly, but there's more. Let's start with the basics. Nanofiltration operates under pressures ranging from 4 to 30 bar. This pressure forces water through the membrane. On one side, you have the feed water, and on the other, the permeate, that is the filtered water. The remaining solution with the rejected solutes is called the retentate.
Okay, I'm with you so far, but how does it decide what to let through?
2 main mechanisms come into play: size exclusion and electrostatic interactions. First, the membrane's pores are around 0.001 to 0.01 microns in size. That's small enough to block divalent and larger ions like calcium and magnesium, but lets smaller monovalent ions like sodium and chloride pass through. That's size exclusion.
So calcium and magnesium get the boot, but sodium gets a free pass?
Pretty much, but the real magic happens with the
nanofiltration membranes usually have a slight negative charge because of functional groups like carboxyl or sulfonic acids on their surface. This charge creates an electrostatic barrier that repels similarly charged ions like sulfates and phosphates.
Wait, so it's not just a physical filter, it's got personality too?
Exactly. The Donan effect is all about how charged particles interact with the membrane's electric field. Since the membrane is negatively charged, it attracts positively charged ions like sodium, but repels other negatively charged ions like sulfates. This electrostatic interaction enhances rejection for multivalent anions and helps balance the ion concentrations on both sides of the membrane.
So it's like the membrane is playing favorites with the ions?
You could say that, but it's not just favoritism. The Donan effect plays a crucial role in maintaining electrical neutrality. For every negatively charged ion that gets rejected, a corresponding positively charged ion often gets rejected as well to keep the balance. This makes nanofiltration particularly effective at separating salts and charged organic compounds.
That's pretty clever. Does the Donan effect work on all kinds of ions?
Mostly, but it's especially noticeable with multivalent ions like sulfates or phosphates. These ions have a higher charge density, which means they interact more strongly with the membrane's electric field. Monovalent ions like chloride, on the other hand, can often sneak through more easily because their interactions are weaker.
So Jamie, between reverse osmosis and ultrafiltration, where really does nanofiltration shine?
Nanofiltration has qualities that are halfway between ultrafiltration and reverse osmosis. Furthermore, Nanofiltration has several advantages over ultrafiltration and reverse osmosis, including a reduced osmotic pressure differential, higher permeate flux, better multivalent salt retention, inexpensive investment, and low operation and maintenance expenses. So, Dr. Nano, what types of membranes are used in nanofiltration?
There are two most used nanofiltration membranes, including ceramic membranes and polymeric membranes. The polymeric membranes have an inferior chemical resistance and have a higher fouling rate, whereas the ceramic membranes have higher chemical, mechanical, and thermal stabilities. Like reverse osmosis, from which it evolved, nanofiltration is also a pressure-driven membrane separation process, which is capable of reversing the osmotic effect of liquids.
Speaking of applications, where does the Donan effect really shine?
Great question. It's especially useful in situations where we need selective ion removal. For example, in water softening, the Donan effect helps remove calcium and magnesium ions while allowing beneficial sodium ions to pass through. It's also key in processes like dye removal from wastewater, where the charged dyes are repelled by the membrane.
And in food processing?
Absolutely. In dairy production, the Donan effect helps separate lactose from whey by rejecting certain charged molecules. It's also used to recover valuable nutrients and remove unwanted salts in beverages and food products. The Donan effect even plays a role in pharmaceutical manufacturing, where separation of charged compounds is critical.
So the Donan effect isn't just a bonus, it's central to how nanofiltration works.
Exactly. Without it, nanofiltration wouldn't be nearly as effective at handling charged particles. It is the unsung hero of the process, quietly ensuring everything stays balanced and efficient.
This is cool. So can I say I'm officially a nanofiltration fan now?
Welcome to the club. Just remember, with great membranes comes great responsibility.
Okay, Spider-Man, let's save the world one filter at a time.